Okay, so we're going to be starting the physics unit today. And one of the big themes that comes up over and over and over again in basically all of our units is the theme of energy. All right? There's lots of different kinds of energy. We'll be focusing mostly on mechanical energy when we are in this unit, okay? But there are obviously other forms. There's chemical energy and nuclear energy, all that kind of stuff, which we'll talk about today. We're going to go over the types of energy, okay, their interactions, and a little bit about thermodynamics if we have time, okay, kind of into all of that today. All right, that'll introduce the biggest concept in all of science, energy, because without it, you can't do any work. Okay, nothing can happen if there's no energy. So that's what we'll be going over that. We'll be starting that today. And then tomorrow we'll probably start into some of the more kinematics related stuff, which is about motion. And then we'll be in motion for a while. We'll look at graphing, things like that for a couple of weeks. And then we'll be back again to energy, work energy theorem, which is the most important concept in science in my mind. And then from there, we'll go to conservation of energy, and that'll be the end of the unit. It sounds short, but it isn't. Okay, we will likely not have a unit exam until just before Christmas. Okay, it'll probably take us until then to finish that up, and then the last unit is pretty short. Okay, so that's kind of where we're headed for that unit. Okay, don't forget that everything I teach you today and tomorrow is not on Monday's exam. Okay, do not study the stuff I teach you today and tomorrow until after the unit exam. Okay, study the unit exam stuff, all the bio stuff we talked about yesterday. Okay, and your plant project, remember that that's coming up due on the 16th. All right, example of energy and conversions of energy is what's in this picture here. I don't think you guys actually have this picture in your notes, but this is of a Inuit blanket toss. Okay. The Inuit used to use this as part of their methods of hunting, okay, things like caribou and things like that. Reason for that is where the Inuit live is in the tundra. Tundra means treeless. It's essentially an Arctic prairie. So imagine Saskatchewan, but in the Arctic. Okay, you know, you can see from one side of the province to the other. Is that flat? That's what the Arctic looks like. Okay, the true tundra looks that way. So there's no trees to climb or anything like that if you're trying to see over the horizon. You can only see as far as the horizon. Well, it makes it pretty difficult to sneak up on prey when there's no cover. So what they would do is they would have everyone in the tribe line up around this big blanket, put the smallest person in the tribe on the blanket, and then throw them up in the air. Okay, that would get them high enough that they would be able to see further. Okay, it'd be like climbing a tall tree, okay, or climbing a small hill or something like that that allowed you to see a little bit further. And then they would be able to spot where a herd of caribou was, and then they'd be able to kind of plan their attack on that and move in the right direction. Right now, in order for the Inuit blanket toss to work, what do the people holding onto the blanket have to do? They what? Okay, they got to hold on really tight, okay? But when the person gets put on the blanket, it's going to pull the blanket down, right? If they want to throw the person up in the air, they're going to have to use some force, right? They're going to have to pull, all right? Now, that's crucial to what we call work, okay? Work is a physical term, not just a four-letter word that you hate doing, okay? It's also a physics term that means to change the energy of something. All right, work, very simply, is a change in energy. We write that most of the time in physics like this. Work equals delta E. Delta means change. Okay, work is a change in energy. So these people who are holding onto the blanket are exerting a force over a distance. Okay, they're pulling upwards slightly. All right, when they do that, they accelerate the blanket and thus the person on it. Okay. What happens to the energy of the person on the blanket? Cameron? Right, they get lifted up into the air. So if they're up in the air above the ground, do they have more energy there than they do when they're sitting on the ground? Absolutely. Okay? I mean, which would you be more afraid of? A piano sitting on the ground or a piano perched precariously on a rooftop? The rooftop, because that one could fall on you. Okay? It has potential energy. It has the potential to fall. And when it does that, it could do work. Because remember, work is a change in energy. And if your energy changes, it's because you're doing work. So if a piano falls off of a roof onto you, it's going to do work on you. It's going to change your shape in an undesirable fashion. Okay? That's work. You don't want that. Okay? That's why you're not afraid of a piano on the ground unless you have some sort of really weird phobia. Okay? But it shouldn't hurt you sitting on the ground. All right? So these people do work, and they change the energy of the person that is on the blanket. They throw them up in the air. Okay? Now, there's a couple of energy changes that go on during that as well. When they first leave the blanket, they're going very fast. When they get up to their highest point, how fast are they going? Slow. Yeah, you slow down as you go upwards in the air, right? Your speed is lost because gravity is trying to pull you back down. So when you leave the blanket, you have lots of kinetic energy, energy due to movement. When you get up top here, you have potential energy because you're not moving anymore, but you could fall back down, and you will, right? So you have the potential to have more kinetic energy when you're up here, right? So there's a conversion of energy types, okay? The initial conversion is the chemical energy of the people. Their food that they ate. That's what's being used to pull on the blanket. They're using their food energy. It's chemical energy. Okay? They're turning that into mechanical energy, the movement of their muscles in pulling the blanket, which is turning into tension in the blanket, which is turning into kinetic energy in the person, which is turning into potential energy in the person. Okay? It's the energy changes forms all the time. Okay? And that's what we have to understand about energy is it's very fluid. In fact, people thought it was a fluid for a long time. We just say it's fluid because it's able to change and flow, okay? But it isn't actually a material. Okay, is everyone kind of follow me there? So what we're going to be looking at in this unit is the interconversions of energy and how that all works. All right. So forms of energy. Okay, forms of energy are the different energy sources, essentially, that we might have or have access to. Okay? So the problem with energy is that it's not a material. And so it was very difficult to measure it, and it was very difficult to look at it, or see it or touch it or whatever, because it's not matter. Okay? Matter's easier. It's easy to deal with. It's concrete. Okay? But energy isn't. And so the idea of energy was a difficult concept for scientists to get their head around, and more importantly, to prove. Okay? Because there was no way to actually see it. Right? So it's very difficult concept to define. Okay? Ask a definition of what energy is, and what comes to mind are the things energy does, the work that we can get out of energy. Right? Like you see, a lot of people, when you say energy, they picture like a lightning bolt. Okay? Yeah, a lightning bolt is a sign that energy is changing. Okay? It's electricity flowing from one place to another, rather arcing from one place to another. Right? It's doing work. And in fact, the only reason you see the lightning bolt is because electrical energy is actually changing form. You can't see electricity. What do you actually see when you see a lightning bolt? Light. Yeah. The electricity is turning into light and heat, and as a result of its disruption of the air, sound. Okay, because lightning causes thunder, right? So we see that the energy that was initially static electricity in the cloud is being converted to other forms. It's doing work, and there's actually, as a result, less energy after the lightning bolt strikes something. Okay. All right. So examples here, they got a person running a marathon. Okay, if you run a marathon, you use up a lot of energy. We say you burn a lot of calories. Okay, when you're running a marathon or exercising in any way. Okay, you're using up chemical energy, the energy from the food you ate. You're turning it into other forms. Okay? What other forms does it turn into? Turns into kinetic energy or mechanical energy, the movement of your muscles and joints and whatever. Okay, and what else? Could be if you're running up a hill. Yeah, up and down a hill, it could be potential energy, yeah. When you're running, you get hot, yeah. Okay. The conversion of glucose into other forms of energy is not 100% efficient. In fact, it's nowhere near 100% efficient. It produces a great deal of heat, okay, which is why we have to sweat and cool our bodies down as a result of exercising. Okay, so a lot of it gets turned into heat. Okay, now, By the 1850s, okay, scientists were convinced of the existence of a scientific concept called energy, but they still were unable to really define it, describe it, okay, because it was an abstract idea, like we said, not a material object, okay. Experimental evidence supported the theory that heat was a form of energy, okay, and that it could be converted into other forms following certain principles. Now, the idea here, this idea that heat is a form of energy, is actually wrong. Thermal energy is what we commonly call heat. Heat is actually the transfer of thermal energy. Okay? When we feel heat, like if you stand next to a campfire and you go, oh, I'm feeling the heat. Yes, you are. You're feeling the transfer of thermal energy from the fire to you, and that's what heat is. In a very technical sense, heat is actually not a form of energy. It's a transfer. You feel the transfer of thermal energy from one thing to another. Okay? So this is actually not so much true. Okay? What we commonly call heat is actually thermal energy. Okay? But they are right in that thermal energy can be converted into other forms. Okay? Thermal energy can be used to do work. Okay? If heat, thermal energy, transfers, okay, from one thing to another, it could energize it. Okay? It could give it more energy and allow it to do something. Okay. Okay, good example of that. How many people have seen the movie The Martian? Okay, a few of you have seen it, read the book. Okay, in that movie, Mark Watney has to go and get the nuclear device there. Yeah, the thermal unit. RTG, right? The RTG. So he has to go and get this thing, which is basically just a big chunk of plutonium that's radiating heat away all the time, and the heat is captured and essentially turned into electricity. Okay, they wanted to bury it because it was radioactive and they didn't want to be around it if it ever ruptured. Okay, but it's what the RTG did is essentially just turned heat into electricity. It was a big giant thermocouple. Okay, that's what we call a thermocouple. It turns heat directly into electricity. All right, so there's practical applications for that, as long as you don't mind being around a big radioactive lump of plutonium all the time. All right, chemical energy. We'll start with that. We'll start with that because it's the one we use all the time. Okay, our entire civilization runs on chemical energy. Okay, if you look at, for example, in Alberta, how we generate electricity. Okay, what's the biggest method of electrical generation in Alberta? Not natural gas, it's up there. Coal, yeah. Okay, the burning of coal is the #1 method of generating electricity in Alberta. It is almost 90%. Okay, if you can believe that. All right, why? Coal is cheap. Coal-fired electrical plants are cheap to build, okay, and we have lots of it. So it makes sense to use it. Is it very clean? No, but it's cheap, and in the end, that's really what it comes down to. Okay, so yeah, we burn coal. We release the heat. The heat is used to turn water to steam, and the steam turns a turbine, which generates electricity. Are there a lot of energy conversions along that path? Yeah, and every time you convert energy from one form to another, you lose a little bit. Okay? You lose a little bit to the surroundings. It gets converted into forms you don't want, okay? Or it's just not a fully efficient conversion. Right? So the more conversions you have, the less efficient, something is going to be. Okay? The way you got to school today, you used chemical energy. No matter how you got here. If you walked, you still used chemical energy, but I would assume probably most of you either took the bus or were driven here. Okay, well, your car is burning fossil fuels. Okay, that's chemical energy. Anytime you're burning something, you're using chemical energy. Right? The majority of our society, of our civilization, runs on that. Okay, now, the idea behind this chemical energy came from a guy named Antoine Lavoisier, and he realized that if he burned different substances, but in equal amounts. So he took, let's say, 2 kilograms of wood, 2 kilograms of coal, 2 kilograms of oil, okay, and he burned them. He found that some of them burned hotter than others. He could get more energy out of some than others, which led him to believe that the chemicals that things were made out of had energy stored in them somehow. Okay? He's the one essentially who discovered chemical energy. Okay, and that chemical reactions, okay, could produce different amounts of heat. Right? That's chemical energy. Okay, when you burn wood, you get heat. When you burn coal, you get even more. Why is that? Where does coal come from? Okay, yes, it comes from the ground. Yes, absolutely. How did it get in the ground? How does coal form? Anyone know? What's that? A lot of pressure and a lot of heat. Coal comes from fossils. Okay, not dinosaur bones. Yeah, people always have that in mind when I say fossil fuel. They picture that they're burning a dinosaur. Okay, actually, coal comes from the remains of plants that lived well over 500 million years ago. Okay, back when the surface of the Earth basically had no animals on it, it was covered in very odd-looking forests. And when those forests died, they fell down, they were buried, sediment piled up on top of them, and more sediment piled up on top. And when that happens, they turn into peat, and then when there's enough heat and pressure, the peat is turned into coal. And there's various grades of coal, but essentially the formation of coal is all the same. It's heat and pressure and organic material. Right? So when you're burning the coal, you're actually burning wood from hundreds of millions of years ago. But it's super concentrated because it's been under heat and pressure for hundreds of millions of years, which is why coal burns hotter than wood. A kilogram of wood and a kilogram of coal don't produce nearly as much heat, right? Because a kilogram of coal could represent an entire tree, okay? At 500 million years ago. So it's more concentrated fuel. Okay, so when wood burns, the energy in the cellulose molecules is released. Okay, that's chemical energy. Chemical energy is a form of potential energy, and it's stored in the bonds of compounds. So if we look at, let's say you're using your barbecue, okay, and you use propane for your barbecue. Okay, so that's propane, C3H8. When you burn propane, you break the bonds between the carbon molecules, between the hydrogen molecules, and every time you break one of those bonds, energy gets released. Okay, everybody follow me there? So it's potential energy stored in the bonds of molecules. Okay, propane is a reasonably good fuel. Okay, we use it to cook things, but when you try and run vehicles off of it, is it as good? Nope. I mean, you can do it, but you lose a lot of power, right? Because typically, vehicles are designed to burn bigger molecules, like octane, which has 8 carbons. Well, if it has 8 carbons, it's got more bonds to be broken. Thus, it's a more concentrated fuel. Okay, making sense? All right, so that's what chemical energy is. It's the energy stored within the bonds of any molecule that can essentially react with oxygen and burn. Okay, now, electricity. Right? Obviously, electricity is important. We use it to run a lot of things. Okay? The ancestor of the modern battery is this. The Volta pile. Okay? You've probably noticed that if you buy like AA or AAA batteries, they actually say like pile alkaline battery on them. Okay? Next time you buy one, look, it'll say that. Okay? Because they are a pile of cells. Okay? Like this was. Right? So it's a we call it a pile because he piled all these discs of metal essentially on top of each other with moistened paper in between, and found that the nature of some metals allowed a chemical reaction to occur if there was moisture there, okay, that would allow electricity to flow. Right? And you'll learn a lot more about that in Chem 30 when you start taking electrolytic chemical reactions and you build your own cell, okay, and things like that. But some chemical reactions will release electricity. Okay? And electrical energy is simply the energy in flowing electrons. If electrons are moving, they have kinetic energy. If we run them through something, they'll transfer their kinetic energy to that object or that machine or whatever it is, and then that machine will turn. All right? So it's essentially, electricity is a transfer of kinetic energy of incredibly small things, electrons, okay, to another machine. All right? Now, do you need to have a lot of electrons? If you want to have electricity flowing, do you need to have a lot of electrons flowing to get any measurable value? Yes. Okay. Like electrons are really, really small. So even though they might be moving really, really fast, they don't have very much mass. So we need a lot of them to get moving in order to transfer charges that can be used to power something. Okay, so electricity or electrical energy is the work done by moving charges. Okay, their kinetic energy is transferred to something else. All right, volta. Okay, okay, the volta pile is made of stacked layers of two different metals. Okay, such as copper and silver, and then there's moistened paper sandwiched in between. The wires connected, and then electricity will flow. Okay, we use different materials now. Okay, alkaline batteries are not made with copper and silver typically. Okay, they're made with other chemicals that yield more electrons. Right, this thing here, the original volta pile would have been probably about that tall. Okay, that would have been the original volta pile, and it would have produced less electricity than a AAA battery. Okay, so obviously we've made the process a little more efficient over the course of time. All right. Yeah, so that was Alessandro Volta's he was the guy that kind of did that type of discovery there, converting chemical energy essentially into electrical energy. Now, other discoveries came once we figured out that electricity flowed and how it worked. You know, Benjamin Franklin got struck by lightning, okay, and all that kind of important stuff. We started to discover that electricity and magnetism were very closely related to each other and that they produced effects of each other. Right? You guys have heard of an electromagnet before, right? Okay, you can turn any metal essentially into a magnet, provided you can run a current around it, okay, and you can produce a magnetic field. So electrical devices produce magnetic fields. Magnetic devices can produce electrical effects as well. Okay, so these two guys are the ones who discovered it. Ørsted, okay, Ørsted did some discovering, and so did a guy named Faraday. Now, what Ørsted discovered, completely by accident, was that electrical currents produce a field around them that produces magnetic effects, okay? Or an electrical field produces magnetic effects. He was setting up an experiment or a demonstration for some students of his. He was a professor, and he had this electrical wire, or current-carrying wire, and he was going to do I don't know what with it. But he happened to have a compass with him for something else, and he had the compass laying on the table. And when he fired up the electricity and the current started running through the wire, the compass went from pointing north to pointing parallel to the wire. It just snapped immediately to parallel to the wire. Now, what does a compass respond to? Yeah, the magnetic field of the Earth. All right. Now, the magnetic field of the Earth is pretty strong, but if you are really close to a wire carrying a high current, it's going to be a lot more powerful because it is closer, right? It's just a matter of scale. It's way closer to the compass, so it's going to interfere with the movement of the compass. All right, you can try that at home as long as you have a non-insulated wire, okay? Which then, of course, you have to be careful with, or you could get shocked, okay? But if you take the insulation off of a wire, the same thing will happen, okay? That's the plastic, rubbery stuff on the outside. Okay? Sometimes even older microwaves will cause a compass to go nuts. Okay, usually the newer ones are shielded a little better, okay, but some of the older ones can cause those kind of effects as well. Okay, actually you can notice that, I notice it with my iPad all the time. If I'm in the kitchen with my iPad and someone fires up the microwave, I got no Wi-Fi until the microwave shuts off. Okay, it can happen. Okay. All right, so Ørsted discovered that electricity produces magnetic effects. Faraday discovered that magnets can push electrons around. And he developed the first electric generator. Okay, so Ørsted developed essentially the first electromagnet, and Faraday used a magnet to produce electricity. Okay, he made a coil of wire and then pushed a magnet through it. And when he pushed the magnet through this coil of wire, it pushed the electrons away from it and caused a current to start flowing. Okay, the electrons didn't like the magnet; they ran away from it through the voltmeter. Right? So what he decided is, if a moving magnet can make electricity flow, I can generate electricity as long as a magnet keeps moving. And essentially, that's how we can generate electricity with like a gas-powered generator. Okay, you just get a magnet that goes up up and down, up and down, up and down through a coil of wire and produces alternating current. Okay, the current goes alternating back and forth, back and forth. Everybody follow me there? Okay, so pretty important discovery, allows us to generate electricity. All right, so that's Faraday and Oersted. They're pretty important guys. Okay, if you hold a magnet above iron filings, the filings move towards the magnet. So magnets, obviously, magnetism is a form of energy because it can cause things to move. Anything that can cause a change in energy in something else has energy of its own. Okay, and then you can say Oersted here. He was the invention of the electromagnet. Okay, and then Michael Faraday showed that the reverse can happen. He moved a magnet through a coil of wire and observed that the electric current would flow through the wire. So Faraday, okay, something like that. Okay, so it was found that basically electricity could be related to lots of different things. Okay, next guy that came along is a guy named Thomas Seebeck. Seebeck developed the first thermocouple, which is what we were talking about here that was in the Martian with the RTG, okay, the big nuclear reactor thing. So what he discovered is you could turn heat directly into electricity provided you had the right setup. Okay, what he built was essentially he took from Oersted's experiment with the compass needle. He said, I'm going to prove that I can make electricity flow by heating something up by putting a magnet underneath these pieces of metal. If a current flows, the compass magnet will move. Okay, so he took a slab of iron and then this kind of loop here made of copper, and he started heating up the iron. Now, iron and copper heat up at different rates. Okay, and when you heat something up, what happens to its particles? They start to move faster. All right. Well, that movement gets transferred along as the particles start running into each other. Okay, if you're heating this end, eventually this end would also get hot. Okay, by conduction, the particles running into one another. But the rate at which the particles move in iron and the rate at which they move in copper was different. So he got a flow kind of going through here, okay, of these particles moving, and that caused an electric current, just enough essentially to move the compass needle. All right, is this a very efficient way to make electricity? No. You don't make very much electricity, and you have to have a lot of heat. Okay, that's why in the Martian he was using a nuclear reactor essentially, which makes lots and lots of heat. Okay, if you recall, he put it inside of the rover to provide heat for himself to keep it, so he wouldn't freeze to death without having to use the batteries. Okay, but he ended up that it was so hot that he'd had to take all the insulation out of his rover. Okay, so he had a huge, huge heat source and was able to get some. They were using it for electricity prior to that. Okay, so we don't typically use this as a way to generate electricity unless we have a lot of heat that we got nothing better to do with. But we do use it to protect electrical devices. Okay. If more current than normal is flowing through an electrical device, the electrical device will overheat, okay, and then it'll burn out. What do we have in place to keep that from happening? Sometimes we have fuses, okay, older things or cars and stuff like that will have fuses. Circuit breakers, okay. Circuit breakers are designed to break the circuit when it gets too hot, and they're essentially a thermocouple. Right? When it gets hot enough, okay, essentially like the spring or the little motor inside that flips the switch open, okay, gets hot enough that there's enough of an electrical current to flip the switch and opens the circuit. With no electricity flowing through the circuit cools down. Right? Essentially, we have them in place to keep our houses from burning down. Right? That's what circuit breakers are designed to do. Keep the circuits from overheating so our houses don't start on fire. Right? That's why you're never supposed to replace a fuse or a circuit breaker with one that's designed to take more current. If you do that, the circuit will get too hot, and then you have a risk of fire. So if it's a 10 amp fuse, you replace it with a 10 amp fuse. Right? Don't replace it with a 20, because then it'll get too hot. Yeah? Okay. So that's essentially what Seebeck found. Okay? Seebeck developed the first thermoelectric converter, or thermocouple. Okay. Nuclear and solar energy. We talked about nuclear energy a little bit in chemistry on the very first day. Okay. The sun is just a really big nuclear fusion reactor, right? But for the longest time, people thought it was something else. Because what does the sun look like? Fire, yeah. Okay, people looked at the sun and went, oh, that's bright. And then they went, but it kind of looks like a fire. So they figured it was just a big fire out in space. I mean, at the time, they didn't know that fire won't burn in space, okay, and that if the sun was actually made of some sort of chemical reaction that would have burned out after 5,000 years, okay, they didn't realize that, okay. But now, of course, we do know that, and we know much more about the sun because we have satellites that are taking pictures of it and measuring it all the time. But we know now that it is really just a big hydrogen fusion reactor. Okay? The sun is so large that its gravitational pull is great enough to force atoms of hydrogen together into atoms of helium. Okay, now that takes a lot of mass and a lot of gravity, but that's how the sun works. Okay, so it is a hydrogen-hydrogen fusion reactor. Okay, right, so that's where our solar energy comes from, because a nuclear reaction produces a great deal of energy. Lots of it is heat, okay, but a lot of it can also be light. And our sun produces all kinds of different wavelengths of light. Okay? The visible spectrum that we feel is important, that our eyes have evolved to use, okay? But also other lengths of the spectrum. Infrared, which is like heat, okay? UV, X-rays, gamma rays, the ones that can fry you or turn you into the Hulk, depending on how you're exposed to them. Okay, that doesn't really work, by the way. All right, but yeah, those are the ones that are the shorter wave ones. The X-rays, gamma rays, UV rays, they're short. Those are the ones that are really, really harmful. Okay, the longer wave radiation, visible light, and heat are obviously less harmful to us. Okay. All right, the other form of nuclear energy is fission, when you split an atom, okay? So fission splitting, fusion is putting them together, okay? But in essence, all nuclear energy is the potential energy stored in the nucleus of an atom. If we alter the nucleus of an atom, we will get energy out of it. Either we break it and we release the energy, or we fuse it with another one and we get energy out of it, all right? Okay, which form do we use on Earth, like artificially? Fission or fusion? Fission, yeah. Fission is, it has a much lower yield, okay, than fusion does, and it's much easier to control as a result. Okay. Fusion has a much higher energy yield, which means it puts out way more energy, but as a result, it's also much more difficult to control, which is why we don't have fusion reactors. It's unfortunate, though, because fusion would be a lot cleaner, right? Nuclear fission involves using really large, unstable atoms that break down on their own and are, as a result, radioactive, whereas nuclear fusion, the waste products are not as harmful. The reaction would still produce radiation, but the end products would be much safer, like helium. Pretty harmless, really, okay, as opposed to plutonium and things like that. Okay. All right, so the solar energy that results from this travels to Earth as radiant energy or light. Okay, so we sometimes call radiant energy light. Okay, and then obviously when light gets here, we can convert it into other forms of energy. All right, if you live in Drake Landing and you got the solar panels on your roof, okay, it's converting some solar energy into electricity. All right, now the thing we're going to talk about most in this unit is motion and energy, okay, or we usually call that mechanical energy. Okay, mechanical energy is the energy that something has due to its movement or its position. Now, this thing here, how many people have seen this thing with the little metal balls that go back and forth? Yeah, okay. So that's Newton's cradle. It nearly got him beheaded. Okay, people were much less accepting of things back in Newton's time. But he got in really big trouble for this because people thought he was a witch. Yeah, well, people believed in that kind of stuff back then. So he pulled, the one ball away, and when he let it go, the ball on the other side flew up in the air. Okay, people looked at him and go, "You're a witch." And he said, "Well, no, you can do it too." "I'm not going to do it. You're a witch." I'm not a witch. Okay, so they were really fearful at that time, right? When when he was about to be kind of beheaded for all of that stuff, he had to come up with an explanation as to why he wasn't a witch and how this thing worked. So that's kind of where the idea of mechanical energy was born, was in his explanation of why this is happening. He said, I give it something when I pull this thing away. And they're like, yeah, you're witchness. But no, it wasn't really, right? He said, I pull this away, well, I lift it up. It's heavy, and I have to, it's work to pull this thing up in the air. And when I let it go, all that work I did gets pushed into the balls, and then the one on the other end receives it, and that's why it flies up in the air. He was, his explanation was at least acceptable enough to allow him to keep his head, okay, which was important because Newton's kind of an important guy in physics, right? But it swung back and forth, and it actually showed a few things. It showed, work or energy could be converted into other forms, because when this thing goes back and forth, you can hear it ticking, which is why it doesn't keep going forever. He really would have got beheaded if it had never stopped, okay? Because then it would have been a perpetual motion machine. That would have really got him in trouble, because that breaks all the laws of physics, okay? But it goes back and forth, and you can hear it ticking. It stops because every time it ticks, it's losing some energy, okay? The sound is not a useful form of energy for the Newton's cradle experiment, okay? It's a wasted form of energy. It's still there, but eventually it wastes the energy that the person who lifted the ball in the first place gave the system of Newton's cradle. Okay, that's why it eventually will stop. All right, so 20 years after that demonstration, okay, a guy named Gottfried Leibniz, who has a terrible name, okay, reasoned that whatever caused the ball to move resembled a force. And he was kind of right. I mean, there was a force used to get it going, at least, right? And it could be transmitted through the balls, right? He called that vis viva, or living force. And that was the first kind of record of anyone having the idea of energy. Okay, this living force was the first idea of energy. Okay. Further to that, he said, there's two different kinds of this vis viva, which we're going to call energy because vis viva just doesn't sound right. Okay. There's kinetic energy, the kind that has to do with movement, and there's gravitational potential energy. He got that idea from Newton, because Newton's the guy who came up with the idea of gravity, right? There's the whole idea that he got hit in the head with an apple, which is just a story he made up to explain it, by the way. It didn't really happen that way. All right. So he's got gravitational potential energy. Okay, an object that's raised above the Earth's surface has the potential to do work because it can fall. Right. So we call that gravitational potential energy. Okay, flowing water, okay, or anything that's moving can do work, and that's what kinetic energy is. That's the whole idea behind a hydroelectric dam. Okay, gravity has given the water gravitational potential energy, and it flows downhill and turns that gravitational potential energy into, okay, well, it's actually always mechanical, but it turns it into kinetic because it moves from a high point to a low point, right? And a river theoretically gets faster, okay, as it goes downhill. So it's turning one form of energy into another. If we then put a dam in front of that river, we allow the natural flow of the river to do work for us. Okay? We turn its kinetic and gravitational potential energy into electricity. Right? Now, we usually build a dam so that it's quite tall and the water has to fall a long way, okay? But we're still converting the mechanical energy of the river into something else. Right? So the sum of these two forms of energy, and that's something we're really going to spend a lot of time on in this unit, is mechanical energy. Okay? So it's possible for something to have both kinetic and potential energy. A plane flying through the air has both. It's above the ground and it's moving. Right? So it has both kinetic and potential energy. All right, is that making sense so far? Okay, so like I said, I highlighted quite a bit more in this motion and energy part because that's the stuff we're really going to concentrate on: kinetic, potential, and mechanical energy. All right, now heat and energy. There's a lot of interrelation between heat and energy because usually when you do work, you change the energy of something else, it's not 100% efficient, and as a result, one of the end byproducts is thermal energy, or heat coming off of that. So thermal energy transferring from whatever is working to the surroundings, and that's why we always call it heat. It's a transfer of thermal energy from one place to another. Okay. So around the same time, scientists are puzzling over what caused heat. Okay, they knew they could get heat from all kinds of different things, but it was usually there was, two surfaces in contact with each other, sliding past each other, or something like that. Okay, the atomists came up with this idea that they had the tiny particles. That would have been, anyone remember who? Anyone remember the Greek guy that came up with the idea? Democritus, there we go. Okay, so the relation to heat and atomic motion was developed long before the 1700s, but they kind of came back to it around that time. Okay, now this guy named Joseph Black, okay, he observed that when a cold object is placed in a cup of hot water and then removed, the object becomes warmer. Shocking. Okay, shocking, right? He discovered that, which, yeah, I mean, in science, that's the beauty of science, right? If you're the first to discover something, no matter how simple, put it on paper, because then you'll get credit for it, okay? No matter how simple it is. Well, Joseph Black is essentially credited with the discovery of thermodynamics. Thermodynamics has to do with the movement, transfer, essentially change of energy, okay? Dynamic means change, and thermo means energy or heat, so this is the movement and change of heat, okay? So he essentially found the second law of thermodynamics. And the second law of thermodynamics says energy flows from high energy to low energy. In his case, hot to cold. You cannot transfer coldness. Okay? People didn't get that for the longest time. All right? If you put a cold object in a hot cup, it's not transferring coldness to the hot. It's receiving hot from the hot. Okay? Yeah, you can't transfer coldness. Coldness is a lack of energy. If you don't have something, you can't give it. Okay? Like that was the problem a lot of people has. Like, well, this has coldness, that has hotness, and they give them no, they don't. Okay? It only goes one way. All right? In order for something to move from one place to another, there's got to be pressure. There's got to be like we talked about with diffusion. There's more of it here, so it naturally goes here. Well, there's more heat here, it naturally goes there. Okay. Now, unfortunately for Joseph Black, he suggested heat was an invisible fluid. Everyone liked all these magical, invisible things that seem to explain everything so nicely, except that obviously we know it can't be a fluid because a fluid would be matter, and then it would have to have mass and take up space. And energy doesn't do that. Energy does not have mass and it does not take up space. All right, so Black mistakenly thought that a substance was being transferred from the water to the spoon, which was very quickly dispelled because the mass of the spoon and the mass of the water didn't change. Okay? If the masses don't change, they're not transferring a material, they're transferring this invisible massless fluid. Yeah, right. Okay, but that's what energy is. It's this massless thing that can move from place to place. All right. Right. So Joseph Black, okay, he came up with this whole principles of thermodynamics, okay, which is the study of heat, work, and energy. All right, and then kind of to his credit as well, okay, the transfer of thermal energy from a hot object to a cold object is heat. So heat is not a form of energy in and of itself, okay, it's the movement of thermal energy. I think I've only said that about a dozen times today. I hope you all remember it. It's kind of important. All right, now, heat and mechanical energy. This is an important discovery as well in that it shows that energy is converted from one form to another. If you have mechanical movement, heat is always produced as a byproduct. Okay, and so this is the discovery kind of that. This guy named Benjamin Thompson, who for some reason changed his name to Count Rumford. I don't know why. He became the Minister of War in Bavaria. His job was to supervise the production of cannons. Now, to produce a cannon, you take a big lump of iron and you bore it out with a big drill. Now, of course, this is before electricity and machinery and things like that. Drills were essentially like an auger. Okay, so a big giant auger that you would use to drill a post hole with, or a hole in the ice with the ice fish or whatever. It's just a big drill bit. Okay, and you had a whole bunch of people that would be on the end of it turning it like this and boring into this big hunk of iron. Now, what would happen to the iron while you're boring it out? It would get hot. It would get really hot. So hot, in fact, that these people could boil a kettle of water on the cannon while they were boring it out. So he has also invented the coffee break. Because if they worked long enough, the kettle would boil and they could make tea. And then they could take a break. Okay, so, but he found that you could only boil the kettle as long as they were doing what? Work. The kettle wouldn't boil when they stopped and drank the tea. Okay, then the heat would go away. Okay, so he discovered there's a tie-in between what his people are doing and the heat that's produced. Okay, no heat's produced if the drill isn't moving. All right, so there's a conversion of mechanical energy, the movement of the drill, into thermal energy. Okay, the heat that's then transferred to the kettle. Not very much, no. Okay, so the idea here is that his mechanical energy, the mechanical energy of the people, is causing the movement of the particles, okay, which is then becoming thermal energy, transferring as heat. Okay, right. So he was the first to realize that heat and mechanical energy were related, and essentially that you could turn mechanical energy into thermal energy. Okay, so people discovered that these were different types of energy. Okay, he kind of had the idea they were related and that they were kind of the same, but that wasn't really true. Where was the energy coming from to make the mechanical energy? The people, exactly. The food they ate, the chemical energy they consumed earlier, right? All of that is just transferring one form or converting one form of energy to another, right? So then this guy came along, Thomas Young, okay? He's kind of more well-known than Rumford, okay? And he took this idea of potential energy and kinetic energy, okay, and he figured out that energy is the capacity to do work. That's the definition of energy. So Thomas Young is kind of credited with defining that. Okay, so essentially that's the work energy theorem that we're going to be spending time on later. In order to do work, you have to have energy, because work is a transfer or a change in energy. So if you're going to transfer energy to something by doing work, that would imply you had to have energy to begin with. Agreed? Okay, like, if your parents say, can you go out and mow the lawn? I got no energy. I don't want to do that. I mean, you really do have energy. You just don't want to. Okay, but if it was true and you actually had no energy, you would not be able to mow the lawn. Okay, or talk or breathe or anything else like that. Okay, but you wouldn't be able to do any work if you had no energy, because work is a transfer of energy, and energy is the ability to do work. So they're tied together. Okay, it's this idea that work and energy go together in that way. All right. Joule. Without a doubt, Joule is the most important person when it comes to energy. That is why the units for energy are named after him. Okay, the units for energy are joules. So obviously this guy had something important to contribute. Okay, Joule really did experiments where he was actually able to measure the energy transfers and quantify it. That was the important step that Joule made. He was able to show, look, I took this, I gave it this much energy, and it became this, and I can show you that it was transferred here mathematically. Okay? I can prove it. That's the big step that turned energy from this invisible fluid stuff that was going on for so long into something real. All right. First off, we had Sadi Carnot. Okay, he performed experiments trying to transform heat into mechanical energy. We know mechanical energy turns into heat easily, but the other way around, not very good. Okay, it is very difficult to convert heat into anything else. Heat is kind of the thermal energy, is kind of the lowest form of energy. Everything turns into it, but it's very difficult to make it do any useful work, right? So thermal energy and its transfer heat is kind of the lowest thing, all right? But what Sadi Carnot found is essentially our kind of rules for efficiency, okay? He discovered, okay, that some heat is always lost, okay, when there's a transfer or a change in energy. Right? No energy conversion is 100% efficient. And that essentially destroyed the idea that you could produce a perpetual motion machine. Right? A perpetual motion machine is supposed to be able to run forever with no input of energy. Okay? But A perpetual motion machine has to convert one form of energy to another, and every time that happens, energy is lost. Then that thing will slow down and stop. Okay. Okay. Now, Joule. Here's Joule's experiments. Okay. The simplest one is this one, the falling block, stationary block impact experiment. What Joule did is he lifted one block up. They were on a pivot. Okay. He lifted one block up, and they let it go, and it smashed into the stationary block, and the thermometer went up. Every time the falling block smashed into the stationary block, the thermometer would increase. Okay? How many people have ever pounded a nail into wood before? What do you notice about the nail in the wood? Yeah, it's warm. Okay? When you pound something with a hammer, you're converting mechanical energy into other forms. Okay? Even if you didn't use a hammer, you just took a piece of wood and, sorry, didn't use a nail. You have to use a hammer. Okay? If you just took a hammer and just banged on the same spot on a piece of wood, put your thumb there afterwards. It's going to be hot. Okay? That energy that you had, the mechanical energy of the falling, swinging hammer, has to be converted into something. It's being converted into sound, and it's being converted into thermal energy, and it's doing mechanical work on the piece of wood. Can you tell where you hit the piece of wood? Yes. You're changing the shape. That's a mechanical energy change. That's work. Okay? So we're changing those forms of energy into something else. So what he was able to do is, with the temperature change, he was able to calculate how much energy was being absorbed by the stationary block, proving that that energy had to come from here, because it only happened when this block smashed into that one. All right? So it proved that energy could be transferred and that it could be converted from one form to another, mathematically proven. Okay? As opposed to, look what I did, which is what kind of everybody else had done up until that point. All right? He had another one. It didn't work quite as well, but he had these pulleys attached to this spinning fan blades inside of a jar, and when the masses would fall, the blades would spin inside the jar, and as they would spin inside the jar, the temperature of the air inside the jar would go up. Okay, so again, he was showing I'm converting mechanical energy into kinetic energy into thermal energy. Right? He was showing that, and then he was able to calculate the exact amounts of energy that were being put in. Okay, everybody follow me there? The other big thing was he proved that an object doesn't have to be moving to have energy. Right? This block, when he moved it up to this position, before he released it, isn't moving, but it still has potential energy. All right? And people had a hard time with that concept. Like, it's not doing anything. It doesn't have any energy. And his argument was kind of the one I gave you at the beginning of class. Which are you more afraid of? A piano on the floor or a piano perched precariously from a roof? Okay? One has the ability to do work and the other doesn't. Right? So that's that potential energy idea that he came up with. Okay, so what I want you guys to do is answer the circled questions only. Okay, I'll give you a little bit time to do that, and then we'll go over them.